Okay, so we're going to try and connect to our iPad and do a pre-recording of our Unit 7, Lesson 3, Similar Triangles. And so you see that here we are, and we're in our new curriculum. Okay, and so we've switched. So we've switched from AOPS to the Mathematics Vision Project. Okay. This is the curriculum being used at Chapel Hill High School in Math 2. And the reason we're switching is that it gives you a different view of some of the math that we're doing, and you'll see that particularly in this lesson. But you'll also see how this corresponds much more closely to the standards. And in particular, it was in dealing with similar triangles that I saw this difference. But another aspect that we're going to see is that it works a lot more on getting you to express yourself about mathematical ideas, which isn't as important an aspect of AOPS. Okay. All right, so for example, in similarity, we had our proofs of similarity based on proportionality and on triangles, and we had our angle, our side, side. But what you'll see is that in the standards, we really have this idea that you're similar if you can define a set of rotations, reflections, translations, and dilations. And so we talked about that a little bit, how sometimes to imagine, so if you remember that triangle that we had, when you have the two right triangles, so if you have the, well, so one time you have this, right? You have this, and so you have a right triangle here, but then you have the other right triangle here. So you get these three right triangles. So you have to rotate them to get them to feel the same. And the other situation we had was with the, was when we were doing the side angle side. And so in one, yeah, so it looked like this. And so if you look at it from this direction, and so we're going to use this same angle on here, but so in one, and so you see, if you have triangle ABC, our big triangle ABC, and then our triangle, so we're going to argue that ABC is similar to ADC. Well, you have to flip it over to get that. So, because they're both using angle A, you have to flip it over so that they correspond. Okay? And so it was kind of similar, but we just talked about, we didn't do it specifically. Okay, so that's something that we're going to see: rotations, reflections, translation, dilations. Okay, so I want to be really strong in this to prepare you for what the NC standards are. Now, part of this is that when Common Core came, they essentially rejected geometry except in terms of using it algebraically. And so even when we're doing geometry here, we're really trying to have relationships that we define mathematically with numbers, rather than the kind of classic geometry that we inherited all the way from Euclid. So let's look at some of these conjectures. I want to think about them. Okay, so all rectangles are similar. Okay, and so what we know and what we've talked about is the idea that if we have triangles, if all the angles on a triangle are similar, then those triangles are similar. So for example, all equilateral triangles are similar, right? So, and I think I can even draw one for you here with explain everything, right? And so if, well, we'll see. We'll see if it considers that a, yep, didn't recognize it. Okay, so let me go into my little store of clip art, and I don't have one, so I'm going to go get one. I think I have one. So we'll see. Let me search if I. No, we don't have one. Okay, so let's go and we'll show you what we can do. So you guys have Explain Everything. So what you can do with Explain Everything, if you're in the middle, is you can just go to your browser and look for equilateral. And usually you don't have to type very much to get it. So you just go ahead and grab it, right? And so, let's grab it and use that select tool there. And we've got it. And then you want to lock the rotation on it. Okay, and so then we say we don't need the browser anymore. And we grab this guy. And you think about it, right? So if I duplicate this, so I say, okay, I've got this size, and then I duplicate it. And we say, oh yeah, so the sides are increasing, they're all increasing at the same rate, right? So there's going to be a proportionality, right? So the base to the base is going to be the same altitude to the altitude. And so we can see that. And so you might say, well, I guess we're going to have the same thing happen with a rectangle. And that's certainly true. So that is one thing we can draw here. So what if we draw a rectangle? And so we draw a rectangle and say, well, okay, we're going to draw a rectangle. And so we draw a rectangle, okay? And then we go in and we duplicate this rectangle. Okay, so we got another rectangle. Okay? And we grab it. And you notice how within explain everything, so yeah, as we expand it, we get, so rectangles can be similar to one another, right? So they definitely can. But what happens though is that you can get another rectangle and say, oh, that's not similar, right? Now, if we copy that and expand it, we can get a whole set of relational ones. So you say, well, yeah, not all rectangles are similar. And now you have to kind of make an argument about that. So what is it? What is it about our triangle that's different? Okay. But okay, all equilateral. What about all isosceles triangles? Are they similar? And when you think about that, you say, well, that's for sure not true, okay? That's for sure not true. And why is that? Okay, so what would your argument be about why all isosceles triangles are not equivalent? And you could, if you wanted to, you could go back to, so see if you remember that chart of the triangles of reality or something like that. So think about that, right? So you have your first name for a triangle. So the biggest angle is acute, it's right, or it's obtuse. And the second name of your triangle is how many sides are equal. So you have scalene, you have isosceles, you have equilateral. Okay? And you think, well, how many of these are possible? Remember, you have a couple that aren't possible. So the equilateral triangle really just has one name. You don't have to say acute equilateral because the other two possibilities aren't possible. But in particular, when you look at isosceles, you say, well, I can have an acute isosceles, right? And I can have a right isosceles, and I can have obtuse isosceles, right? If that's in the middle. So clearly those are not similar. Okay. But they also don't have three angles that are equal. Okay. And so what we see is that for any triangle, we have the sense that if the three angles are equal, so think about that, and we'll talk about those in class, those conjectures. Those are things that you want to do. So I could give you my conjectures, but you also want to just work on your own, see if you can make your own conjectures. Now, here's what they're going to talk about is can you always dilate? So the argument is that, well, I could rotate and then line up, say, point A with point Q, and then I can dilate, okay? And, in that case, it's easy to go back then to a diagram like this and say, yeah, we can overlap these, right? I can put this on here, but you can see that we'd have to if we expand this by dilating, which is exactly what happens, right? When you do it and explain everything, we're not going to it's not going to get that shape, right? So its proportions are completely different, right? So you're not going to be able to dilate and get those same proportions. Okay. Now in this one, they're saying, well, we're going to rotate until the vertex coincides, right? So what are they saying they're going to do? I think they're going to rotate that over there, or maybe rotate and translate. So I'm going to rotate and translate. Okay, and at that point I can dilate. Okay. And so I'm going to use this point and dilate from there. Okay, and so what we'll get then is, so remember, we know what this angle is, right? If it's a equilateral triangle, it has 60 degrees. So basically, the dilations of that 60 degrees just keep going out, right? So you can make dilations like that. Okay, so one thing you should think about is that both people are making mathematical arguments. However, one is wrong. And so just because you can make an argument doesn't mean that that person is correct. And that's something that they're trying to build. And we didn't see as much of that in AOPS. So, and it's something that's going to be a little hard to build even in our Zoom setting, right? So it's a lot easier when you're actually in person and you can sit and try and convince each other about these things. We might try it a little bit in class, okay? And so we'll talk about these conjectures. And so, and you might even be able to, you know, and so you think about a diamond and a square. So square is a rhombus, but it seems a lot different than a diamond. Okay, and so what is it? What is it about? Well, not all angles are equal. Okay? So we can have a rhombus and a square with the sides being equal, but the angles are different. You can have the rectangle. Okay, you know, the rectangle, right, with all the angles equal, but they're not similar. Okay, and so here is the AOPS definition. So the AOPS definition says two polygons are similar if all corresponding angles are equal and corresponding pairs of sides are proportional. Okay, and so that helps you to see that in Mason's argument, we have the angles being equal, but we don't have a proportionality, right? So we don't have that same proportionality. So that's necessary as well. And so we do have that proportionality. So as you do the dilation of the equilateral triangle, you get it. Isosceles triangles, well, you can show isosceles triangles where the angles aren't the congruent. Rhombuses, angles not congruent. Okay, squares are similar. Okay, so you can have that. Okay, so let's go to number 8. And in number 8, we say two triangles are similar if their corresponding angles are congruent. And so what if we try and use their technique? Well, so if we begin by translating, okay, so we're going to say, okay, we're going to put this guy down here. So we've got those angles equal. And then as we dilate, we're just going to keep going out along these rays. And so we can create any triangle. So depending on the dilation, we can create any triangle. And if you recall from our book, okay, so remember what we did in our book. We proved that these sides have to be parallel to each other. Okay, so we proved that they were parallel. And so now we look at 10. So 10 is the AA similarity, okay, that we worked on. And so you might say, so we have kind of a simple argument to say why that's true. So let's see if we can copy that diagram from, see, so I'll go in and erase what I did here. And we'll grab it, and so we'll copy it. Okay, and so when we copy it, we just say copy, and we'll go to the next, and we say paste. And okay, so there we have it. And let's lock the rotation on that. And we lock the rotation. Okay, so we can grab it and move it around, but we've got locked the rotation. Okay, and so we have angle A, the same. Okay, so we better lock this guy as well. Okay, so let's see what we've got. We've got angle A equivalent to angle D, and DE is the same factor bigger as AB as AC is bigger than DF. Okay, and those seem to be corresponding if we look at them. Okay, so now, what do we really know about this? So now what we have is what we called in the other book, we called this the side angle side. Okay? And basically what you're saying is that you could actually place ACB in here, right? You could place it in here, and you're just dilating. So it's similar to that argument that they're making. Now, what if you prove that you have three sides that are proportional to each other? What do you think? Are they similar? Is that sufficient? If you have three sides that are similar, and what would your argument be? So you think back, well, we had SSS congruence if three sides were equal. And so that seems to be something that's possible, right? So it doesn't seem impossible. And so SSS similarity okay, and so you might want to say, well, why? How would you prove that? What would be your argument for that? Okay, so that's a good thing, and we can see if anybody has a good argument for that. Okay, and so let's just go ahead and we'll see what your homework looks like. Okay, so we're going to add a file in a front box. And look at your homework, and so that would be lesson 3 lessons. So we go back and we say homework, and we see lesson 3 similarity homework. So here it is, import it. Okay, so you can see that you're not in AOPS land anymore. So these are pretty easy proportions here. Okay. Okay, all right angles are similar. All right triangles. Okay, well, so remember we looked at that diagram of the different kinds of triangles that you can have. Okay, and then okay, so I think this is a nice manageable project for you.